Hi everyone, this is Module 5. Today we're going to be talking about causation. So, epidemiology can really be boiled down to the study of cause and effect. We talked last week about comparison, allowing comparison of how an outcome changes based on a certain exposure. But in order to do that, you have to have the study of some cause and its effect on something else. And so here, of course, in this little cartoon example, the cause is the injection, the effect is the tears. Think of epidemiology as detective work, essentially. You're going to try to build a case that some factor, some risk factor, some exposure causes some outcome. But usually, it's not an open and shut case. There are very few outcomes that we're interested in, usually diseases, but they can be other things too, that have a very clear single cause. Heart disease, for instance. Well, lots of things cause or contribute to heart disease, but it can very rarely be said that this person had heart disease because of smoking, or not exercising, or a poor diet, or genetics, or whatever. A whole host of factors contribute to cardiovascular disease. So it can be quite complicated to figure out what the cause is for various effects. And so really in this module, we're going to talk about how we determine how strong evidence is. Does X cause Y? How sure are we? And how do we know how sure we are? So again, cause and effect is the principle that we want to talk about. Sometimes other terminology is used. I've talked about exposures and outcomes a lot this semester so far. Those essentially mean the same thing. If you've ever had a research methodology class, you may have heard it called an independent variable and a dependent variable. An independent variable is a variable that affects another variable. The dependent variable is the one that depends. It's the effect. So I just want to make sure that if you hear this terminology, you know what we're talking about. These are just other words for cause and effect. So in epidemiology, in real life, sometimes it can be really hard to know if X causes Y, if this causes that. They may be related, but we don't know if one actually causes the other. If they're related or associated, that can be valuable to know, and that's the start of epidemiology, is finding associations or relationships. But then we want to take it a step further and determine if one causes the other. It's all well and good to know about cancer that, hair color is associated with developing cancer, but we want to know if hair color causes cancer. If they're related, that doesn't help us prevent cancer. If hair color causes it, that can help us treat and prevent. So remember, you've seen this slide before. The number of students who wear chacos is correlated to the average exam score on anatomy exams. So this is a correlation or a relationship or an association. All of those words mean the same thing. But does that mean that wearing chacos causes you to perform better on an exam? Or does performing better on an exam cause you to wear chacos? Probably not. That doesn't really that doesn't make sense. And yet, it's not uncommon with other less obvious examples to see people saying, this thing causes this other thing because they're related. Well, that's a mistake. We have to be very careful to not assume that one thing causes another if the research shows that they're related. Correlation does not necessarily mean causation. So what does mean causation? How do we know if an exposure causes an outcome? So here's a couple of examples. Say you have a theory. The number of storks in a certain location affects the birth rate. This movie came out on Friday. Looks pretty fun. So, yes, this is a silly example, but it's also a pretty good example. Does the number of storks in the United States, is it associated with the birth rate? Does it cause a certain birth rate? So how could I test this theory? We've talked about study designs, so I want you to think through what the best study design would be and what the easiest study design would be. And I'm guessing that hopefully you could come up pretty quickly with the fact that the easiest study design would be a cross-sectional. We could look at the number of storks in each state and look at the relationship between that number and the birth rate in those states. Or we could look at the number of storks in the United States and the birth rate in the U.S. and compare to storks and birth rates in Europe. But that doesn't necessarily mean, even if there is a relationship, that the number of storks causes the birth rate. There could be some other variable that's related to number of storks and birth rates that is actually the true cause. The best way to study causation is to use a randomized control trial. But would that be the best use of resources? Randomized control trials tend to be pretty expensive and time-consuming. Is this really what we want to know? Do we really want to study storks and birth rates, or would our resources be better used to study what causes cancer, what causes diabetes, maybe some more public health issues? You could argue all day about that, but it's just important to keep in mind that we can't test everything with a randomized control trial because resources are limited. So here's another example. This is a real-life example. There's a drug called clofebrate that was found in the 60s to be related to, it seemed to lower triglycerides, cholesterol and triglycerides. And so that sounds really good in terms of heart disease. So there was this theory that clofebrate reduces heart disease mortality. Maybe it would save lives. This was the idea. So again, this drug, it had been noticed that it reduced cholesterol, and so that begs the question, could it reduce myocardial infarctions? Those are just heart attacks, and therefore could it reduce death from cardiovascular disease? So that's a very important question, probably worth the resources. So a randomized control trial was done. These are very famous trials. And the randomized control trial did show an effect of the drug on lowering both cholesterol and triglycerides. These are both risk factors, known risk factors for heart disease. So if the drug can lower these, that's good, right? However, they also noticed increased early death in the participants, the people who got the drug. The study was supposed to last 5 years, but because of this early mortality, they decided to actually increase the length of the study to try to figure out what was going on. So the average person in the study was followed for over 13 years. And they ended up concluding that even though clofebrate lowers cholesterol and triglycerides, for some reason it actually increases cardiovascular disease mortality, which is, of course, not a good thing. But we wouldn't have known that without the randomized control trial. We found there was a relationship between the drug and cholesterol, but just because there was a relationship between those two things doesn't mean that there's a causal effect on reducing mortality, and we wouldn't have known that without the trial. So, randomized control trials cost lots of money. They take a long time. In this study, 13 years. So, how do researchers decide when to conduct one? That's really what we're going to be talking about today. How do we know when it's appropriate to do a trial? Is there a way around doing a randomized control trial? A cheaper, faster, easier way? But definitely you have to know that there's an association between two variables before you take that step forward to do a randomized control trial. And you have to decide that the outcome, in this case was heart disease mortality, is a big enough problem to investigate and to invest a lot of time and money into. Here's another one that this is a very classic epidemiology topic: smoking and lung cancer. We all grew up being taught that smoking is bad for you, especially for your lungs. Okay, so there's this theory, it started in the 1940s, that smoking causes lung cancer, but it was very poorly understood, and the Surgeon General didn't make a warning until the 1960s about smoking. So how can we test the hypothesis? In this case, well, we could do the cross-sectional study. Is there a relationship between number of cigarettes smoked and lung cancer prevalence? But remember, the best way is to do a randomized control trial. Well, in this instance, it would be unethical to do a randomized control trial. The reason for this is that if you suspect that cigarette smoking is dangerous for your health, it would not be appropriate to randomize half the people in your study and tell them, go smoke. You can't do that. If you wouldn't be able to give people a drug that you knew was going to hurt them. You can give them a drug that you think might help them, but not a drug that you think might hurt them, or not a cigarette in this case. So, there's actually never been a randomized control trial demonstrating that smoking causes lung cancer, because it's unethical to conduct a randomized control trial. So in these types of scenarios, can we be confident that smoking actually causes lung cancer? Is this causal relationship between smoking and lung cancer that you've probably known about since you were a young child, is that really true? In this case, we think it is, scientists think it is, but it's not based on randomized control trial. And so what we're going to be talking about is, how are physicians, scientists so sure that smoking does cause lung cancer when they haven't done a randomized control trial? So there are what are called causal criteria. These are criteria that are used to suggest a cause and effect relationship between two variables. I'm sorry, this slide is kind of appearing strangely, but a scientist named Dr. Hill came up with these criteria in 1965. There are 9 of them, and essentially you can look at each of these criteria and decide if the relationship between the two variables meets any of these criteria. If it meets all 9 of them, then it's more likely that X does cause Y. If it meets none of them, very likely X does not cause Y. What if the relationship between the two variables meets 4? Well, there's no magic number. It's very subjective. And so, even though it's pretty much agreed that smoking causes lung cancer, there's still no magic formula. We are for sure confident because of this. It's a subjective process. Here are the 9 causal criteria. We're going to go through these one by one. Okay, so the first of the causal criteria is strength of association. So strength of association says that the rate of disease is higher in the exposed group. So, for instance, with the smoking and lung cancer, there would be a higher rate of lung cancer in people exposed to cigarette smoke compared to those who are not exposed. So, the rate of disease, odds ratios or relative risks are rates of disease. So, say the odds ratio is 12.5. That's a strong association compared to, say, 1.5. The stronger the larger the odds ratio or the relative risk, that's a stronger association. So if smoking is strongly related to lung cancer, we can be more confident that it causes lung cancer than if it's weakly related. An odds ratio of 1.2 some pretty small number, we can't be very confident in that because there could be bias, there could be just a random chance. A very high, large odds ratio or relative risk makes us more confident that the two variables are causally related. So here's an example. You've seen this data. This is made-up data. You've seen it before. What it's showing is cigarette smoking as a risk factor for lung cancer and for coronary heart disease. Okay, so the relative risk for cigarette smoking causing lung cancer is 14. The relative risk for coronary heart disease is 1.6. So based on this information alone, I would be more confident that smoking causes lung cancer than that smoking causes coronary heart disease because the strength of association is so much higher for lung cancer. The second causal criteria is called consistency. This is when the association is repeatedly observed, especially by different people in different places, different circumstances, different time periods, and so forth. So if you find that smoking is related to lung cancer in every continent in the world, and this was true in the 1900s and the 1950s and today, and different researchers have studied it, and in different ages, different socioeconomic groups, different races, you'd be more confident that smoking causes lung cancer than if all the studies were done in the same decade by the same scientist in the same part of the country. That would make you not as confident. Okay, so all of the cross-sectional studies that exist out there on smoking and lung cancer show an association. They show that those things are related. That is consistent. A different example, some studies have shown that oral contraceptive use is related to breast cancer, but other studies show that those two things are not related. There are even a couple of studies that show that oral contraceptive use decreases risk of breast cancer. So if some studies show a relationship, some don't, some show a negative relationship, that does not make you particularly confident that oral contraceptives cause breast cancer. The third causal criteria is specificity. This says that the association between the variables is limited to one disease and a single group or location with no other likely explanation. So this one is that definition isn't super clear, but I think the example really helps. Asbestos is a chemical that was used, especially in building a lot of homes. There's still certain tiles. It was in sheetrock, and so there were buildings, locations, homes where people were exposed to asbestos. So asbestos causes a very specific lung disease that's easy to distinguish from other lung diseases. Okay, so if you have a certain lung disease, you can tell this was caused by asbestos exposure. But lead exposure is associated not with a specific disease, but with just low IQ. Therefore, it's more difficult to show that lead causes low IQ because lots of other things cause low IQ or are related to low IQ, like low socioeconomic status, for example. So, if the outcome is not specific, low IQ is not very specific, whereas this, I don't remember the name of it, this lung disease that's caused by asbestos is very specific. So it's easier to establish a causal relationship for the very specific outcome. The next causal criteria is called temporality. This has to do with time sequence. This says that the effect must occur after the exposure. The effect has to come after the cause. This is especially true for diseases that develop slowly over time. So here's an example of this one. There have been studies, cross-sectional studies, that show a relationship between blood pressure and calcium levels in the blood, serum calcium. But just because those two things are related, we don't know which one causes. It could be that higher blood pressure causes you to have higher calcium levels, or it could be that higher calcium levels cause you to have higher blood pressure. It's not known which is which. And you have to know which one comes first in order to determine the cause and the effect. It's the chicken and the egg problem, essentially. There's also an issue with latency. This is how long it takes for a disease to develop. So the example here is low cholesterol is associated with increased risk of colon cancer, but we don't know if the low cholesterol causes the cancer to develop, or if the low cholesterol is a marker of early colon cancer. Colon cancer takes many, many, many years to develop, and it's usually not recognized until it's a fairly later stage. So, because of that long latency, that makes it difficult to know which came first. Alright, the next causal criteria is called the biological gradient. Sometimes this is called a dose response as well. Those terms can be used interchangeably. This says that more exposure should be associated with a higher rate of disease if the relationship is causal. So the best evidence for causality is a linear gradient. So if you increase by X amount of exposure, you get X amount of more disease, and so on and so forth. So here's an example. You've seen this data before. Distance walked. This was the Harvard alumni study. So people that walked less than 5 kilometers per week had the highest mortality rate. If they walked 5 to 10 kilometers, they had a lower mortality rate. If they walked 10 to 20, slightly lower, and then even greater. So it's kind of like a stair step. The more exposure, which was walking in this case, was associated with reduced risk of disease. It could be higher risk of disease. In this case, it was lower. But either way, this is a dose response. More of the dosing that's the walking. More walking had a greater effect on the disease. The next causal criteria is called plausibility. If something's plausible, that means it's possible, or it makes sense. So this says that findings are explainable by existing biological knowledge. Smoking, it makes sense that smoking could cause lung cancer because you inhale smoke into your lungs. It does not make a lot of biological sense that ingrown toenails would cause lung cancer because toenails and lungs are not particularly related as far as we know scientifically. So that's an example of plausibility. Does it make sense? Basically, does the science even make sense? The next causal criteria is coherence. This says that a causal interpretation should not conflict with knowledge about the natural history of the disease and its pathophysiology. So if X causes Y, does that fit into what we know scientifically? Does that fit with the greater body of knowledge about science? Experiment is the next one. This is when you manipulate the cause and it alters the disease. So this is basically a randomized control trial. That's what you're doing with an RCT, is you're doing an experiment. If I influence the exposure, I give people a drug, perhaps, then I can measure the outcome. Does manipulating the cause alter the rate of disease? If it doesn't, then it's not a cause. So if you think that eating carrots causes skin to turn orange, then you could do an experiment where you give people carrots, and if it really does cause skin to turn orange, then you should see that change happen. If it doesn't cause it, you won't see people's skin turning orange. And then the next causal criteria is analogy. This says that weaker evidence might be accepted as causal if similar exposures or risk factors have already been demonstrated to be a cause of the disease. So maybe you show, a common example of this is you show in an animal model, like a mouse or a rat or a monkey, that something causes a certain disease. Well, if it happens in an animal and then you show it in a human, those are analogous. That would help demonstrate that X really does cause Y. Okay, those are the causal criteria. Again, very rarely is an association between two variables going to meet all of those criteria. Maybe there's 5 criteria that it meets. Maybe there's 1. Maybe there's 8. There's no magic number that tells you when you're confident that the exposure really does cause the outcome. You just have to consider all the evidence as a detective would and make a thoughtful decision of whether you believe the cause really does affect the outcome. One thing to be very cautious about is called confounding, and I wanted to mention this. Confounding occurs when you see an association between an exposure and a disease, but it's because of a third variable that you're not studying. So, for example, say the mortality rate in City A differs from the mortality rate in City B. Maybe we're looking at Tampa, Florida versus Los Angeles. The mortality rate in Tampa is a lot higher than it is in Los Angeles, but does that mean that location causes mortality rate? Does that mean that living in Florida is causing people to die? Well, we've seen something similar to this example before, where age is a factor here. Perhaps the overall population in Tampa is considerably older than it is in Los Angeles. Well, in this case, age might be confounding the relationship between location and mortality rate. And therefore, you would need to be aware of age when deciding if location causes mortality rate. Okay, so in a causal situation, an exposure comes before the outcome and is related. It causes it. In a confounded relationship, you still have your exposure and your outcome, but there's a third variable here. The third variable has to be related to the exposure and the outcome, but it's what's causing the exposure and the outcome to look like they're related. If you didn't know about this confounder, it would seem like the exposure is causing the outcome, but it's really not. The confounder is causing it. So let's give some examples. First of all, to be a confounder, there's 2 criteria that have to be met. The variable that might confound has to be a risk factor for the disease, and it has to be associated with the exposure, but not a cause of the exposure. So that's what you see here. The confounder is a risk factor for the disease. That's why the arrow is going towards the outcome or towards the disease. See the double arrow here? This shows that the confounder is related to the exposure, but it doesn't cause it. The relationship goes both ways. These 2 things are related, but one doesn't cause the other. Okay, so let's give a real example that will help make sense. Coffee and pancreatic cancer. Some research showed that there was a relationship between consuming coffee and developing pancreatic cancer. But our favorite risk factor, smoking, might confound this. So let's decide if that's true. Smoking first would have to be a risk factor for the disease. So is smoking a risk factor for pancreatic cancer? If it is, it might be a confounder. The other thing that has to be true is this second bullet point. Smoking has to be associated with coffee consumption. And that's true, it is. People who smoke are also more likely to consume coffee, but smoking doesn't cause people to consume coffee. So, smoking meets both of these criteria. Okay? Is smoking a risk factor for pancreatic cancer? Yes. Is smoking associated with coffee consumption? Yes. But not caused by coffee consumption? Yes. In that case, smoking is a confounder. And so you would have to take into account whether people smoke or not in order to study the relationship between coffee and pancreatic cancer. All right. I want to just walk through very quickly the 4 study designs that we've talked about and how these relate to causation. Remember, cross-sectional studies are the weakest study designs. We can use cross-sectional studies to get an idea of the strength of association. You can calculate odds ratios. I'm sorry, that's not true. You can calculate what's called a correlation, which we haven't talked about yet, but you can get an idea about the strength of association, and you could possibly get an idea about dose response or biologic gradient, but there's a big problem in cross-sectional studies with confounding. So these are not particularly good for showing causation, but they can be good for helping identify topics that should be studied in other ways. Case control studies, there's a big problem with what's called selection bias. We mentioned this a little bit last time. Sometimes when you pick cases and you pick controls, you might accidentally introduce some bias that you don't even realize. Say you pick some rare disease, you get everybody who's being treated at a hospital for that disease, and then you pick your controls from people who are also being treated at a hospital for some other disease. Well, maybe there's something about being treated at a hospital that affects you in terms of the outcome that you're measuring. That can be, selection bias can be a big problem. Temporality, remember that's the chicken and the egg, which comes first. That can be a problem with case control studies. So these are, they're a little better at showing causation, but they're not by any means. Cohort studies are good at showing temporality, because remember, with a cohort study, you enroll people and then you watch what happens over time, particularly or usually many years. They can be good at showing dose response as well. Make sure you consider the timeline for a disease to develop. If the disease takes a long time to develop, like colon cancer was the example, then it can be a little less clear if something's really a cause or if it's just related to that condition. And then the randomized control trial is the best at demonstrating causation because it's an actual experiment. This is really good at getting at dose response because you can provide different levels of intervention. In physical activity, for instance, you could have people do 3 days a week of exercise versus 5 days a week, and you could see, does disease risk actually decrease with more activity or not? The randomized control trial is so good because it minimizes confounding. The randomization that you use, the blinding that you use, minimizes. Okay, that is the material for this module. This week you have a quiz as usual. You'll also need to post in the discussion board number 3 for the week. And this is the last of the material that will be covered on your first exam. I'm going to post an exam review for you by Friday, and then we won't have a module next week. You'll be spending your time preparing for the exam. I will also give you some information about the format of the exam when I post the exam review. But the exam will be in class. You must show up to take the exam in class on Wednesday, October 5th at 1 p.m. It will be just the regular class period, 1 to 2:50 on Wednesday, where you may take the exam.